All right, well, happy Monday, everybody. It's good to see you. And it's already week 4, so things are picking up and we're moving right along. Okay, we've covered a little bit of base Python, and I thought, I want to get into Numpy. There's an important data structure in Numpy called the Numpy array. Base Python has its own array, which is, useful for storing, just for kind of like storing some data. But if you want to do any kind of mathematical operations with it, definitely Numpy is the way to go. And so we'll cover that. And so as far as Numpy goes, if you've installed Anaconda, you will Numpy will be gets installed along with Python. But you can always you might have to install it yourself using Conda or pip. And then when you start a notebook and things like that, you will have to import Numpy in order to make use of it. Okay. And so when you import Numpy, this is the convention that everybody follows. All right. And technically in Python, when you import a module, you can, this part where it says import, module name, in our case, import Numpy as something, you can technically put any word you want here, okay? Any set of characters you want. But the convention is NP, and that's what everybody does. And if you don't do this, people will get confused reading your code. So just follow the convention. Import Numpy as NP. I think maybe the official pronunciation of this is Numpy, but I don't know. It sounds weird to me. Numpy. But anyway, so you do this, okay? And you can kind of just check what version you have installed on your machine, and you can do and when you write pi, I'm assuming pi, but it could be it's ambiguous, right? So 119.2 is what I have. You can always update on your computer as well. So you can always, I don't know what the latest is, but you can type in conda update numpy, and it will go through the process. And let's see, I probably don't want to do this right now. Okay, but anyway, it's got to figure out what a lot of things have dependencies. So I'm just curious what it's going to do. Let's see. Oh, there's an inconsistency. Uh-oh. All right. Well, it'll figure that out. All right. And so anyway, what NumPy introduces is the array. Okay. And so, you get access to the array by doing np.array, much in the same way that you do, like once you do import math, you can do math.py, math.square root, math.whatever. In this case, once you import numpy as np, you get access to the functions inside numpy using np dot. And in our case, we're going to use the numpy array. All right, I want to cancel this. And so these are a few ways to do this. You can also kind of create a list using square brackets, and then you'll put that list inside the array. And so this is an example, right? So here we can create an array out of the list that contains the elements 1, 2, 3. And here we go. Here's it says an array, and the values are 1, 2, 3. Now, when the output is an array, it looks like this. When you print the array, it's going to get printed like this. All right. So this is the appearance. This is how an array looks, and you'll notice it uses square brackets, but there's no commas in between the values. Okay. Whereas if you just have a list, it gets printed out with square brackets and there's commas. And so this is kind of just by looking at the printed object, this is how you can differentiate between an ordinary list with values in it and a NumPy array. Okay, look at all of this. What's the latest version? Oh my goodness. Something. Okay, well, we're not going to do this right now. All of these dependencies, we're going to say no for now. I'll do it later. I do recommend running conda update -- all periodically to kind of update your packages to the latest things. And, you know, on data camp, you should go through to kind of make sure that there's a lesson on using conda and setting up environments, which is helpful and handy. Okay, so that's what it says. Printed array has no commas, and a printed list does have commas. And, you know, if we check what is the type on this, if you say type on A, it's going to come back and it's going to say it's an ND array. All right, and so that's how we know that's not a list, but it's an array. So the key difference between a list and an array in Numpy is that Numpy arrays, the values all have to be of the same data type. The values all have to be the same data type. And so, so what it will do is it will upcast, or if you're coming from R, we call this coercion. It's going to upcast the data type to kind of the least restrictive data type, okay? So in our case, I have an array, and what I'm doing is I've got a list. Inside this list, I have integer 1, integer 2, floating point value 3.0, and Boolean value false and true, okay? And so the floating point value is the least restrictive data type, and so everything else gets upcast to this, right? So the integers 1 and 2 get upcast to floats, and we can tell that they're floats because it has a decimal point. So everything now has a decimal point, and it goes 1 point, 2 point, 3 point, 0 point, and 1 point. The false got upcast to a 0, the true got upcast to a 1. All right. So I think this is behavior that if you're coming from R, you're accustomed to. And if you've not, you know, all of you have seen R, but if you haven't seen R, you know, this is kind of a newer, like, it's a bit of an unusual feature. Okay. Here, we have the number 3, but it's a string. Okay, so it's a string with the 3, and so everything will get upcast into strings, and so the integers get upcast into strings, and true and false also get upcast into strings. The array structure is also used to hold a multi-dimensional array, you know, like a matrix, right? So here we have a 2 by 3 matrix, okay? And this is achieved by calling array upon a list of lists, okay? So here I have 2 lists of length 3 inside a larger list. And when I call array upon that, then I have the result is a 2 by 3 array. And so here, I have basically 2 square brackets to open and 2 square brackets to close, right? So this outer square bracket is the entire matrix. And then this thing is kind of the first row, and this is the second row. And the fact that I've got 2 here indicates that it's going to be a 2-dimensional object. It's a 2-dimensional, I've got rows and I've got columns. Right. So, you know, when you print this multi-dimensional array, it's going to do this. If you have an array, if you have a list of lists, but the dimensions do not match, then you'll get an array of lists, which is a little bit strange, but this is what we have. So here I have a list, an outer list, and inside I have 2 inner lists, but the inner lists do not match. This one is length 3, this one's length 2, and so this will create an array, but it creates an array of lists, right? And here, you know, it gives me a warning. It says creating an ND array from ragged nested sequences is deprecated, right? So it says, you know, this is allowed, but pretty soon this is going to go away. All right, right now it's deprecated, and deprecated just means if you have this code in existing code, you better fix it, because eventually we're going to stop supporting this this change, and then your code's going to just result in errors. Right? So do the lists have to be rows, or can you tell Numpy to make them columns? Let me think. I mean, there's a transpose function, but I'm trying to think. So, I mean, you might be able to provide them in columns and then transpose it, but I want to say when you have a list of lists, it's going to treat them as rows. But perhaps in the creation, there's a, I probably have to check the Numpy. Let's see, shape, float. Okay, so. Right, all right. Object array like be true order can false. All right. Okay, yeah. So you can specify, put it in, I guess, column order, row major, or column major, C or F. You can specify in the order of this thing. You can set order equal to something, and it will that's the feature that you're looking for. Okay. Other ways to make arrays, and so these are just kind of handy shortcuts to just kind of make a quick array that's going to be pre-populated with things. So you have the zeros, and you give it basically some kind of dimension structure. And so here I said 0 is 5, and this will make a one-dimensional array of length 5 of zeros. Okay. By default, it's going to create floating point values, but you can say the data type I want is integers, and it will make it integers as well. Okay. You can here inside this zeros function, instead of giving it a single value, which would correspond to kind of the length, you can give it a tuple. Okay. A tuple of however many dimensions you want. And so here I give it a tuple 2, 4, and this basically says make an array, 2 rows, 4 columns, and of zeros. And so I've got a 2 by 4 matrix of zeros here. Here I give it a tuple of length 3, which this is going to be a 3-dimensional array. Okay, this says 2 layers, and each layer has 3 rows and 4 columns. Okay, so basically I've got kind of this rectangular prism structure, 2 levels. Each level has 3 rows, 4 columns, and you can see it right here, right? And so out over here, I've got the three opening square brackets, and then this is one row. Here's another row. Here's another row. 2 square brackets close off this first layer, and then 2 square brackets opening and close the second layer, and then finally the 3rd square bracket closes off the entire array structure. All right, is that okay? This 3-dimensional array here, which is 2 by 3 by 4, and so so one thing to note is the order of the dimensions in Python in Numpy is different from the order of dimensions in R. Okay, so R I think will do, if you give it 3, it'll be rows, columns, and then layers, but then here it's layers, rows, and then columns for 3-dimensional arrays. Okay, here is a 4-dimensional array, 2 blocks, 3 layers or 3 sheets. Each sheet has 4 rows and 5 columns. And you can kind of see that structure here. So here's kind of your first block, which is 3 by 4 by 5. Here's your second block, that's 3 by 4 by 5. And this, I guess we would call this a hyperprism, a hypercube, something like that. I don't know. But anyway, it's possible. So that's NP zeros and whatever you want. There are kind of equivalents, and there's NP ones and NP full, which is basically the same thing as NP zeros, except NP ones will fill it out with ones, the numeric 1, and then NP full you give it the fill value. So you say, you know, I want to use 1.2 everywhere or something, and you can do this. All right. And if you want to have random values, there is also Numpy comes with kind of random generation things, and that will be our next lecture as far as filling out a matrix with random values. Okay, let me give you your first view quiz answer for today. Is the letter D. D as in dog. D as in dog. Okay. All right. Oh, I'm sorry. I got ahead of myself. Yeah, the random numbers are right here. So if you want to generate matrices with random values, you can do np.random, and this will give you access to all of kind of the random things. All right. So by default, NumPy uses the Mersenne twister, which is kind of this well-accepted way of generating random values. It's the same random generating function used in R, but you also have choices. You can always go NumPy random. Open. Let's see. Go to the manual. So it looks like okay. So you got all sorts of stuff, and you can kind of read these things. But here I'll just kind of cover the most most commonly used ones, right? So one is if you know, anytime you use a random generator, I often recommend using some kind of seed for reproducibility, right? So if you want somebody else to kind of reproduce the same results as you, you can do np.random.seed, and then you just specify a number to specify what you have, and then the default kind of your random function, this will generate random uniform values, is random.random. So you do numpy.random.random, and here I do 5. And so this will generate 5 random values inside some array. And again, just like with numpy.1s and numpy.0s and things like that, you can give it, you know, a tuple of dimensions to give you, you know, a matrix of values rather than some kind of just a one-dimensional array. All right, so this is random. This will give you random uniform on the interval 0, 1. You can also do rand n. Rand n is for random normal, and this will give you values from the z distribution with a mean 0, standard deviation 1, and we got this. Oh, how interesting! We got negative 1.654, which is basically your 5th percentile. So we almost have exactly the 5th percentile here, but you know, other values right here for random normal. Okay, and then you know, as far as random normal goes, if you can also generate values not from the standard normal, but from some other normal distribution. So here I'm going to specify values from a normal distribution where the mean is 10 and the standard deviation is 3, and I give it a tuple of dimensions here, which says, you know, I want it in 2 rows and 4 columns. And so here we have an array where the output is. Okay, lots of other random generation functions. You have random int. Okay, rand int will give you values from 0 to 10 exclusive. Okay, so this is basically integers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you know, basically your starting integer to your ending, but not including this one. And then this is how many values you want, or you know, a tuple of dimensions to do that. Okay, so this will do that. You can, you know, if you want to simulate dice rolls, you can do this. This will be like 1 through 7, 1, 7, which will give you the integers 1 through 6, things like that. Okay. Here's the, whoops, I should open this in a new tab here. So here's a whole bunch of documentation as far as any of the others. Yes, so these are all sampling with replacement. There are ways to sample without replacement. So let me, I think sample, let me see. Random underscore sample. Let me see. Simple random data. You know, just like everything else, we'll go to Google. Without replacement. All right. Random choice. Generates a sample from a given one-dimensional array. Okay, so here, if you want to do random sampling, random choice, right? So again, Google is your friend and the documentation is your friend. So always, you know, whatever you're trying to do, just type in NumPy, you know, whatever it is you're trying to do, you'll probably find it here, okay? So here, yeah, replace equals true. You can change it to replace equals false, and it will sample with or without replacement for something like that, okay? There's lots of random distributions you can choose from. So I just showed, you know, random uniform on some interval and random normal. But, you know, if you want to generate values from the beta, binomial, chi-squared, Dirichlet, exponential, whatever, all of these are kind of coded in there. Is that good? Any questions on random sampling, which is always kind of helpful and handy? All right. You can make sequences, ranges, just like in regular Python. Okay, so you have np.arange for a range, but in an array, right? And it works exactly the same as, you know, regular Python. So the regular range Python object will be start, stop, which is exclusive, step size, right? And if we do this, this will go 0, 2, 4, 6, 8. All right. If we do it in NumPy, it's basically the exact same thing. Okay, I do numpy.arange 0, 10, 2, and I get an array 0, 2, 4, 6, 8. Right. So these two things work almost identically, except range creates a range object that you can throw into a list, but you can also take the range object and throw it into an array, and it will produce the same result. Okay, but you can just also do it in one function and call numpy's arange function, rather than calling range and putting it into NumPy array. All right, and so here, you know, 0, 105 will go, you know, count up by 5s up there 95. You can also, probably very common, you just call NumPy arange 20, and it will just give you a length 20 array starting at index 0. So that's all, that's very, very handy, right? Okay, another very useful function is called linspace, right? And so a lot of times if you want to do some kind of plotting, you know, anytime you plot things, you need kind of a sequence of x values, and then you compute the y function for all of those sequences. And so linspace is very handy. And so you can specify the starting value, the stopping value. In linspace, by default, the stop value is inclusive, and then the length of the array that you want. Okay, so here, if I say linearly spaced values, we want to start at 0, we want to end at 100, and because 100 is inclusive, starting at 0 and ending at 100, I'm going to have to ask for 11 values, and this will space it out at 10 apiece, right? Now, if you don't think about that and you just say, you know, I want to go from 0 to 100 in length 10, okay, it'll do 10 values, but in order to get 10 values to include 0 and 100, it will make your step sizes 11.1, okay, and it works, but there you go. If you want, you can also specify endpoint equals false, okay? And so this will basically say, all right, we would want to go from 0 to 100, and the endpoint is false. And so basically, it kind of does the calculations for here. It kind of does the calculations as if you wanted to get 11 values, but then we're going to exclude the last one, and then we would step up by 10. Okay. But notice this is kind of strange. Okay. If I say 0, 109 endpoint equals false, everything is spaced out by 11, 1.11, and the endpoint here, the endpoint for this one, 0, 110, it ends at 90, whereas 0, 109, it ends at 88.8. Okay, and so the way that these things are calculated is by first it's assuming endpoint equals true, it adds 1 to this, and it does the calculations for how far apart these things should be spaced, and then it drops the last one. Okay, so 0, 109 endpoint equals false is basically doing 0, 110 to get this spacing, and then it drops the last value. Okay, and then 0, 110 is basically doing 0, 111 to get this kind of spacing, and then it drops the last value. So that's how you end up with 90 over here and 88.88 over here. Okay, I think it's better to just keep in mind that the endpoint is inclusive. But I know it's a little bit strange just because a range or the normal range object, the endpoint is always kind of exclusive. But that's just something you gotta remember. Okay, so arrays. So basically, in NumPy, both your single one-dimensional vector and the matrix is all handled with NumPy array. Okay, which is a tiny bit different from R. In R, you had atomic vectors, and you also had matrices, and you know. Matrices had dimensions, but atomic vectors did not in R. Okay, in NumPy, everything's an ND array. Everything will have dimensions and shapes and things like that. Okay, so n dimension is the number of dimensions. It's going to say this is a one-dimensional array, this is a two-dimensional array, this is a three-dimensional array. Okay, shape is the dimensions itself, right? So if it's a two-dimensional matrix, it's going to, the shape will have the values of how many rows and how many columns you have. If you have a one-dimensional array, okay, the shape will contain the length of the of your one-dimensional array. Okay, and then data type was, you know, what kind of value is stored in the array, right? Because in the array in NumPy, all the values have to be of the same type. And we like arrays in NumPy that have this restriction that everything has to be of the same value type because, well, it makes things kind of behave a little bit more predictably. And it also just greatly increases or speeds up your processing power. Okay. In a list, you can do math with lists. You can do addition and subtraction and things like that. But it's going to be very, very, very slow for big lists. Whereas NumPy arrays are very rapid and quick. All right, so anyway, here is, I'm going to just create a simple 3x4 matrix X, right, of the number ones, okay? And these are all floating point. And so if we check all of these attributes, okay, number of dimensions, this is a two-dimensional array because it's got rows and it's got columns. The shape is 3 rows, 4 columns, okay? And so, and it returns a tuple with the shape, 3 rows, 4 columns. And then the data type is going to be a float. Okay. And here, technically, NumPy supports different floating point values. You can, the default is 64-bit floating point, which is, you know, the max value is around 10 to the 308 power. But you can also have long floats, which I think is float 80. And you can also have single precision floating, which is float 32. So those are all supported. You know, if you have strict memory kind of management ideas and requirements. Okay, here is another array that I'll create here. This is a one-dimensional array, all right? And it's going to go from 0 to 11, and so it's length 12. Okay, so if we ask the number of dimensions, this is one-dimensional, all right? It only has a length. It doesn't have the number of rows or columns, it's just the length. And so the shape is going to be a tuple, but it's a length 1 tuple. Okay, it's a length 1 tuple, and we know it's a tuple because it's got a little comma after the 12. Okay, so it just says the length is 12, and that's it. Okay, so it comes back with the length 1 tuple, and well, if I asked y dot data type, it would come back and say it's integers. Okay, let me go ahead and give you your next quiz answer. Where am I? It's 4th week Monday. Okay. Next quiz answer is C. C as in cat. C as in cat. 4th week Monday. C as in cat. Okay. All right. So we can reshape the arrays. All right. Reshaping is very handy. You take your current array, you reshape it, and it's going to return a brand new array. It doesn't take the so okay, and so we'll take a look. All right, so here is J. J is going to be a one-dimensional array, length 12, and we're going to call J. We're going to ask reshape on J. Okay, we're going to do numpy.reshape J, and we give it the dimensions, and we say, you know, I want it to be a 3 by 4. Okay, and so when we do that, this will return a new array K, or it's new array, which we are going to assign to K, and that's going to be 3 rows and 4 columns. And notice the when it reshapes row-wise, right? So that's kind of the default way it does it in NumPy, which is different from Python. I mean, and which is different from R. R, if you reshape an atomic vector, which you're allowed to do, it fills it column-wise. Okay. And when you call numpy.reshape, the original matrix or the original array is unchanged. Okay, so J still remains a length 12 one-dimensional array. Okay. But you can also call array.reshape, and this will actually, when you call the method array.reshape, so if I call j.reshape, that will affect J. Okay, so here if I call j.reshape, and I say j.reshape 4, 3, then it produces an array. It will reshape J itself to be 4 rows and 3 columns. Oh, I'm sorry. I'm mistaken. And yeah, I have that mistaken. And J is left unchanged as well. Okay, so it just returns a reshaped version of J. I apologize. I thought it made a change. Okay, so j.reshape 4, 3 will reshape J and return the reshaped array, which is 4 by 3 here. Okay, so here's K. It's 3 by 4. Oops. And then you can also call transpose. K.transpose .t is the transpose. So .t is a this is an attribute, okay, and it just kind of takes the array and it just transposes it, just exactly as you would expect. But the calling the transpose will not modify the original array K. Okay, so K.transpose is just, it's an attribute, and it just takes the array and it just transposes. Right. So I think this is one nice thing about. Not one nice thing. This is a really nice thing about Python arrays. I think K.G, this is easier to read and as seeing it as transpose, because it mimics kind of your matrix notation and math and stuff, versus in R, you always have to call T parentheses on the matrix and things like that. Okay, is that good with everybody here? All right, and so not everything, but a lot of these things in Python will return an array, which means we can chain the methods together, okay? So np.arange is going to create an array. The array has kind of the attribute or the method reshape, and that itself returns an array. And so then I can just ask for the transpose. So here I can call np arrange 0, 12. that creates a length 12 array. I can reshape that to be 3 rows and 4 columns. And by default, Python, when it reshapes row-wise. So it's going to fill out the row 0, 1, 2, 3, 4, 5, 6, 7 on the second row. Third row is 8, 9, 10, 11. And then I can call .t, and then it does that, right? So this is all done in one line of code. And all I'm doing is I'm just chaining the methods using the dots. So run a range dot reshape dot t, and I chain these, right? So this is kind of a nice thing that you can do. You can kind of, and if I wanted to, I can do dot after this, because the object here itself is an array, and so I can continue chaining more methods. So I can do dot t dot t dot t dot t, add in, you know, as long as I want, and it'll keep working. All right, there's no limit. You know, all of these things keep returning arrays, and you can kind of chain all of these methods together. Okay, so so here is okay. So sometimes we see when you do reshape, sometimes you'll see a -1. Okay, yes. So I don't think I have an example of that here. Okay, so this is a very good point. So a lot of times you will see a -1, and that just means the person was a tiny bit lazy or didn't want to, wanted to leave it flexible as far as reshaping the array. Okay, so this is a good point here. Yeah, that's a good example here. So let's do, let's call J. All right, so we'll do J. All right, and so you can also do j.reshape, and you can say, you know what, I want to do, I want whatever I want. I want it to have 3 rows, okay? But maybe you're not sure exactly how many columns you have, right? So you just want to reshape it to 3 rows, and so you can use the -1, and the -1 just says figure out how many columns will be appropriate to make sure that you have 3 rows, okay? So using -1 for a dimension, we'll ask Python to figure out the number to use for that dimension. Okay, so j-reshape will do that. You can do j.reshape, you know, -1, and you can say, you know, I want 4 rows, and it'll figure it out. So you just have to supply at least one of these things, right? So you can do 2, comma, -1, comma, 2, and it will reshape it into a 3-dimensional array, and it figures out, okay, if you want 2 sheets, some unknown number of rows, and 2 columns, right? So this is 2 sheets, unknown number of rows, 2 columns. It does that. Is that okay? Are you guys able to see this? Okay, what's going on as far as using the -1 as far as reshaping an array? So yeah, thanks for bringing that up. I forgot about. That's good. Let's try to run all of those things. Let's save that. Put these things to slides. All right, so these are those examples of using the -1. Okay, so -1 for dimension, Python will figure out what number needs to go in here. So you can specify, you know, I want 3 rows, figure out how many columns. I want 4 columns, figure out how many rows. You know, I want 2 sheets and 2 columns, you figure out how many rows, right? So you have that, okay? If you ask for a 1-dimensional array and you ask for the shape, it gives you this tuple. right? A length 12. It says it's length 12. It's one dimensional. If you ask for the transpose of this, okay, so this is a behavior that is different from R. If you take in R, if you take a vector and you ask for the transpose, it's going to create a matrix out of it. Okay. In Python, here it says the transpose of this ends up is still just a length 12 vector. There's no second dimension here. This is not a 12 by 1, right? This is not 12 by 1. It's just 12. The dimension is length 12. It doesn't see this as a matrix. It just sees this as a one-dimensional structure. And so the transpose of a one-dimensional structure is still just one-dimensional. Okay. And so if you ask for the transpose, what's the shape of this? It's still just one-dimensional with a length of 12. Okay. On the other hand, if I take this the same thing and I reshape it to be one row, 12 columns, okay, now it's a two-dimensional structure. It's a 1 by 12. And if I ask for the transpose, it becomes 12 by 1, right? And it reflects that. When you ask for the transpose and ask for the shape, it's going to say it's 12 by 1. Okay, versus over here, this is truly one-dimensional, and the dimensions or the shape of this is 12. 12 comma nothing. Over here, now we have a two-dimensional structure. This is one row, 12 columns, and you can transpose that, and you'll get a 12 by 1. All right, if you you can subset the array and slice it just like you would subset and slice a list. Okay, so you can say, what's the fourth index 4 element. So this is the fifth element in the thing, and you can also ask for the elements between 4 and 6, and you'll get an array. Okay, you can also slice with another column or another colon with array. You can do the start location, stop location, and the step size. And so here you can say, I want you to slice from position 1 to position 8 with a step size of 3, and it will pull the values 1, 4, 7. Okay, here I created take the A range, and I'm going to say start slicing from the very beginning, so I don't give it a starting value, up to 100, step size 2, and this will pull out all of the even numbers. Okay. I could have just as well created the A range myself by specifying 0, 100, 2 with a step size 2, but you can slice it that way. So, okay, you can slice in higher dimensions, much like you would subset a matrix in R, in that you specify what rows you want and what columns you want. Okay, so here I'm going to create a 3 by 4 array. All right, so I have 3 rows, 4 columns, and you can say, I want index 1 for the row, index 2 for the column. So index 1 for the row. So remember, NumPy is 0 indexed. So this is the 0 row. The index 1 row is the middle, and the index 2 row is the bottom. And the index 2 column is basically the third column. So the index 1, index 2 coordinate will give you the value 6, right? And when you subset using this, if there's only one value, it's no longer an array. It's not a single array. It's just going to be the integer value. All right. So if you subset it to just a single value, it's just going to be the integer value. It's not an array that's 1 by 1. Okay. Over here, if I subset and I say, I want the rows 0, 0, colon 2, which is basically going to be the first 2 rows, and 0, colon 2 for the columns, it's going to return basically this top little corner, this square in the corner, right? And it gives that. And this is clearly an array. It's obviously a two-dimensional structure, 2 by 2 thing. Okay. If you say I want row 2, and then you put in nothing, well, not nothing, but you put in just a colon for the columns that you want, it will give you the entire row at index 2, right? And this NumPy, it'll do is it will kind of reduce the dimensionality, okay? And so this is not a 1x4 array. It is a length 4 array. It's a one-dimensional structure of length 4, right? So NumPy, when you subset it down, it will reduce the dimensionality. So basically its simplest form. So if you subset it down to one value, it'll just be that data type. If you subset it down to one row or one column, it'll be a one-dimensional structure of that length, right? And then if if what you subset is basically a small rectangle, then it will retain the array structure. Okay, so here I say I want the index 2 column, which is going to be 2, 6, 10, and we can also see that this is a one-dimensional structure. It reduces it down to one dimension here. Okay. When you slice a NumPy array, the slices are view objects. Okay, so if you remember the dictionary view objects that just get automatically updated as the original dictionary updates, the slices update as well. Okay, so here we're going to just start off with a 3x4 array. Okay, and I'm going to subset it to this top left corner, 0, 1, 4, 5. Okay, and then what I'm going to do is I'm going to modify the top element in Z, or the top left element from 0, the 0, 0 element to 99. Okay, and you'll notice that this top left, this Z underscore sub, okay, still references the object Z, okay, and this value has changed to 99, okay, even though I didn't like reassign it, okay. This is not, when I say subset Z to basically 0, 1, 4, 5, I'm not creating a new copy. I'm not creating a copy with the value 0, 1, 4, 5. I'm creating basically a view, a 2x2 view of the Z object. So when Z gets updated, this subset, the view object, also reflects that. Okay, and so this will change to 99. Does that make sense as far as what's happening? Okay, and so this points to the object Z. Now, if I came back and I just said Z is equal to a brand new array, then the corresponding view object will not get updated because it's now a brand new object in memory, right? Here I'm modifying. I'm just kind of saying I just want to change this top left number in this one object to 99. Okay, so Z, the object Z, the top left value is 99, and this is just kind of the view of the top left corner. All right, so here I'm just creating a brand new object. Okay, this is not here I created an object and I created a view of this. Okay, over here I'm creating a brand new object. I'm calling NumPy a range, and I'm reshaping it to a 3x5. This thing is not modifying Z, okay, or not modifying the object, the original 3x4 object where I changed the top left corner to the number 99. I'm not modifying that. I'm just creating a brand new object in memory, and I'm saying, you know what, let's also call this Z, okay? So when I call Z, it looks like this. And so when I look at the view object of Z underscore sub, this is still pointing back to the 3x4 object in memory where the top left corner is 99. I hope, did that make sense? Let me know if this doesn't make sense as what's happening. So here I just created a brand new object. So this thing, Z sub, still views this object over here. So here I created this object. I modified the top left corner to be 99. And so Z sub is, providing a view of that. And we are not modifying it here. We're just creating a brand new object that just happens to be called Z. Okay. And so now that this is kind of the case, I don't really have a way to kind of change these things anymore. Okay. I mean, I can change them via Z sub. Okay. But the object that exists in memory that has other values over here that there's no name that points to it anymore. Okay. Okay. If you don't want a view object, you can always use .copy. And I know I'm going over my time here, but .copy will do this. And so here I can say, take the top left corner, .copy. And then here, if I change the top left corner to 55, obviously it's not changed because it's a copy. Okay. Even though Z has been changed to 55, that top left corner has been changed to 55, the copy doesn't reflect that. Okay. Whereas over here, if you change, so here's my view object, right? Here's Z. My view object is going to be the top left corner. We're going to change the top, the 0, 0 object in the view object, 0, 0 element in the view object to be 99. That also changes the underlying array here. Okay. So the view object is basically something that you can modify the view object directly, and it will modify the underlying thing. Okay. So we call these things view objects because they update dynamically as the underlying object gets updated. Okay, let me give you the last view quiz answer for today. Last view quiz answer for today is B. B as in bear. B as in bear is your last view quiz answer. All right, so, and then, yeah, view objects themselves are arrays, and they have all the kind of methods and attributes that go with arrays as well. All right, that's kind of our first intro to Python. We'll see, not Python, NumPy, and we'll see more NumPy stuff on Wednesday. So we'll see you then. Have a good night.